Hi, welcome to this channel. So today we are going to discuss on a very small but a very important feature in STAAD. Now this feature I have selected after receiving several requests from some users as this topic is not properly covered in some important sources. Now the topic that we are going to discuss is on the vertical seismic load effect. Now, most of you might have used the static seismic for defining the lateral loads for a building or any other industrial structure. Now, this is very straightforward. All you need to do, you need to define the static seismic load definition, then the seismic weight through the mass modeling or by directly defining the seismic weight, and then directly defining the static seismic along the two different lateral directions. But how about if you want to define it in the vertical direction? Now we could not define it directly along the vertical direction just like we do it for the conventional horizontal load application. But there is a way around to do this. So today we are going to use the ASCE-7 code just to discuss how to define the vertical seismic load effect. So if you go to the code and go to the equation 12.4.4a under the chapter 12.4.2.2, this is on vertical seismic load effect. So what it states that the vertical seismic load effect, which is expressed as EV, shall be determined in accordance with this equation. That is, EV is zero point 0.2 times SDS times D, where the SDS stands for the design spectral response acceleration parameter at short period obtained from section 11.4.5, and D is the dead load effect. Now, unlike horizontal seismic load, which is calculated using the multiple set of equation uh, and have a specific vertical load distribution mechanism, the vertical seismic load are very straightforward and relatively very simple. So as per this equation that we see here, it is basically the dead load being factored by zero point 0.2 times SDS and D is the dead load. So what we need to do, we need to know the value of SDS and D. D is the dead load, so it's a normal structure which has the gravity load, and this is the dead load which is already defined. What we are going to do is we use the reference load case to call the dead load, and then we will use the SDS factor. Now, SDS factor we don't have to calculate manually. The good news is there is a way out to quickly know this SDS factor. As in this model, we already have the static seismic load case defined along the lateral direction. So if I run the model and go to the output file, so you can see here, uh, yeah, this one. This is equivalent seismic load as per IBC 2006. So I have just used this 2006. You can use any other version of this code. Now here you can see all the parameters as per the code are calculated because we already defined the uh, seismic load definition. And from there, this SDS value are fetched. Here you can see. So note down this value, and we will use this value to generate the vertical seismic load. So we are going to add a new primary load case, keep the loading type as seismic V, Now you could use it without defining this loading type, but it is always suggested to do. The reason being, if you tag those loading type, program can identify this loading type and it would be used for generating the automatic load combination. So I have generated a new load case here. Let it be like seismic vertical. And if I go to add, there we have it's not the reference load, it should be the repeat load. Uh, we will now call dead load here and factor it. Now this factor is the another component which is present in the equation, that is 0.2 times SDS. So you need to multiply 0.2 with the SDS value that you have fetched from the output file. Now, if you recall that the output file reported the SDS value of 1. So my factor would be 0.2 times 1, that is 0.2. Had it been some other SDS value like say 0.25, then you should have multiplied 0.2 times 0.25, and whatever would have been the product of this, you should put the factor here. So in our case, it is like 0.2 times 1, that is 0.2, and hence we are defining it here. So now let's run the model. So here you go. So this is the static seismic response. If I see the deflection, you can see it is on this direction on the lateral orientation, and this is on the other orthogonal direction. Both of them are in the lateral direction, and this is our vertical seismic. Okay, now this is just an example where a simple model is used. You can use the same approach for your real life model, may it be building or any other complex industrial structure. So that's it for today. So this is very short, but that could have been a very important information for your STAAD project. So please stay tuned till a new video is being released. Thank you.